Welcome back to our automotive testing series. Today we are talking about how we test and validate ADAS systems. ADAS stands for Advanced Driver Assistance Systems. When we test an ADAS system, we cannot just look at the vehicle computer, the ECU itself. ADAS behavior is a team effort. Sensors detects things, network sends the data, the ECU makes a decision, and the car reacts. Professional validation means we follow this complete signal chain to verify how the entire system behaves. Our main job is to prove that the whole chain works correctly under control. Let's trace this signal flow here inside what we call the telemetry dark room. First, there is a physical stimulus like an obstacle on the road scenario. The sensor interface detects that particular situation. This data travels through the vehicle's network using Automotive Ethernet or CAN-FD interfaces. The ECU processes the data and makes a decision which leads to an actuation command like actuating braking or applying the PB. As test engineers, we must verify every single transition in this chain to make sure no data is being lost. Here is our first practical scenario. A vehicle is 40 meters away, but the car does not brake. We must ask, is the ECU actually defective or did the signal never arrive? Before we blame the software, right, we must check the input. Did the simulator send the radar messages correctly? Like that question we should ask. Was the cable connected other side? If the signal never reached the ECU, it is a test environment problem, not necessarily a software bug. A good validation test converts a written requirement into measurable signals. Okay, here is our requirement. If you could look at the screen, the system must intervene when the objective relative velocity is over 30 km per hour at a distance under 15 meters. To test this, we convert it into three exact signal criteria. That means we break down. So for distance, one signal, relative velocity, one signal, and then AEB command, one signal, and its conditions are given. Now we build a repeatable test case using 4 steps. First, we control initial conditions like toggling parameters to set up our vehicle speed. Second, we define precise stimuli, setting the signal amplitude to 2.5 volts and the frequency to 300 meters per second. Third, we set strict timing tolerances like a cycle time of 50 milliseconds and a jitter of 0.7 microseconds. The fourth one, the last one, we establish expected verdicts like the expectation with a clear pass fail range between 0.5 with a tolerance of 0.5 and 1.5, the range. Here is another scenario. You try to run your test, but you see an alert. Simulated radar node offline. This alert came. We must ask in this case, did the ECU fail the logical test or were the prerequisites are missing, like preconditions are missing? Since the simulator was offline, the test could not execute. This is not a failed test. It is called a blocked test. Keeping these two terms separate, for us, it is crucial for clean quality reporting actually. So blocked is different, failed is different. To trust our test results, we must monitor the test environment as carefully as we monitor the ECUs. On our test benches, we check 4 main things basically. The supply voltage is normal or not. Communication buses are connected and active or not. Like CAN, LIN, FlexRay, whatever the communication is chosen. Simulator timing must run in real time. Around 200 microseconds cycle is good to maintain. Synchronization should be there. It should be locked actually. should not be like disruptive. It should be locked like with a GPS or PTP. A simple pass or fail grading is not enough in this ADAS testing. We must inspect the raw signals that are passing through, because no, the telemetry is the evidence beneath that particular verdict. We will use an oscilloscope and a CAN trace viewer, mainly the CAN vector CAN tools we use. We can check the exact timestamps and latency of that particular data. These raw traces are the solid engineering proofs. They are the logs that show exactly how the system has behaved while analyzing. It will help the development team also. Here is a common mystery on the test bench. The emergency brake, if you could see, the emergency brake signal arrived 80 milliseconds late. There is a gap of 80 milliseconds. We then ask a question, right? Is the delay caused by simulator lag in the test bench environment, or by the scheduling logic inside the ECU? Where does this gap comes? So if it is environment side, we must align our timestamps. If the input signal itself arrived late to the ECU from the models, the ECU is actually not the one to blame. We have to think about environment. So we should fix. Let's clearly define our three validation verdicts here. Pass means the observed behavior met all of our acceptance criteria defined. Fail means the test executed correctly, but the ECU behavior violated the existing requirements. Then blocked is a special case where it means we could not complete the test because a prerequisite or a piece of equipment was missing. Using these three terms, pass, fail, blocked, correctly, we are going to keep our reports highly professional as an ADAS validation engineer. This is one of the most important rules in validation. Always separate ECU defects from the environment issues. If you see an ECU defect, that is a real problem inside the ECU, like a software bug you found, or an incorrect decision algorithm is detected, or a state machine error could be seen with automation. Then comes another part where environment issues, they are like outside problems, not the software bugs. So a broken cable, because of a broken cable there is a deviation, because of a simulator lag, it is not passing, unstable power supplies. These are all environment issues. We must always use signal evidence to prove that root cause. Once proved, then only defects can be raised. Let's look at this in practice. The vehicle does not brake when it should. Let's say the vehicle does not brake when it should brake. What we will ask, did the logic fail, or is the ECU correctly rejecting a malfunction signal? Let's say we again check the logs. If the input signal has corrupted or stale timestamps are there, the ECU is doing the right thing by rejecting it. That's an environment issue actually, not an ECU software bug. So it's like bad input. When a test fails, we perform something called RCA. That full form is root cause analysis. To find the exact technical reason, we follow four clear steps. First, identify the symptom, then extract the timestamps from it, and then correlate the logs across our system, sometimes requesting the manual testing. Then we isolate the component at fault level. We do not stop until we have the timing is aligned with the proofs that are there. So defective documentation. Once we prove a real software bug exists, we must write a clear defect report. Here is our main job starts. A professional report includes software version, ECU configuration, and precise production steps, how you done the test, and what is the expectation, what is the actual behavior, attached signal traces, and their timestamps. Everything will be under one place. So this helps the developer understand and fix the bug quickly without guessing it. So there is no assumptions. Everything is there. Before we send a report to the software team, we again have to ask another question. Is this a credible ECU defect or an isolated environment suspicion? Like, are we suspecting it? We run the exact same test multiple times on our hill bench. If the failure happens every single time under the same conditions, we are confident it is a real software bug. If it only happens once and disappears in the second run, the problem is likely there is an unstable test bench arrangement. We must look it. Let's say once the software team delivers a fix, they accepted our defect and they delivered a fix. We again follow a two-step process. Here the job is reduced, but two-step process. Here we in step one we will flash the corrected software build onto the ECU. Then in the step two we execute the scenario that was failed, and now we must verify that the specific failure is completely gone and is passing before we do anything else in the testing here. ADAS unit. A successful retest is not the end of the road here. We must run regression testing to prove that fixing this bug did not accidentally break another part of the system, like delta testing we can call it as. We do this by testing boundary conditions, some neighboring use cases, or you can say fault injection techniques, affected interfaces. Here you say some decision based testing. So this builds a solid wall of evidence proving the system is still stable, nothing is broken. So to finish our validation journey today, we write the final report. We close with this core principle in our mind. Professional validation is not about making every test pass. It is about producing reliable evidence, correctly identifying failures, proving the root cause, and verifying the correction. This is how we build true engineering confidence. Thank you.